Feasibility module. Hello everyone, my name is Alberto Marquez. This video focuses on the feasibility analysis specific as suggested by the Port Planning and Investment Toolkit of the U.S. Department of Transportation and the American Association of Port Authorities. A feasibility analysis process is carried in two steps: measuring and evaluating. Measuring includes the physical and operational performance, market and financial performance, impacts, and risk. Evaluation comprises the evaluation approach, the comparison of reasonable alternatives, and finally, the recommendation of the project. Measure. For an investment feasibility analysis, a port's individual capabilities, markets, and competitive relationship is studied. It is also necessary to identify the physical, operational, commercial, political, and financial metrics that will govern project success. Feasibility analysis typically include measuring economic and non-economic benefits, as well as cost of the project alternatives. Benefits include capability or capacity, positive impacts and revenue generated by the project alternatives. Costs include operating and capital costs, finance costs, and negative impacts or unintended consequences generated by the project alternatives. Feasibility analysis relies on the appraisal of quantitative and qualitative measures involving project implementation and completion. Quantitative values include performance, capabilities, impacts, costs, benefits, competitive factors, and risks. These results come from using analytical tools and are used to characterize a project alternative performance. Some qualitative values are used to assess the social goals, institutional goals, and regulatory imperatives which cannot easily be quantified. There are 4 areas that are required to establish quantitative and qualitative performance of a project alternatives that include 1. Physical and operational, 2. Market and financial, 3. Impact, and 4. Risk. Physical and operational analysis measures the physical capacity and/or productivity of each project alternative and determine whether they support the forecasted demand. Market and financial analysis determines whether each project alternative improves the port's ability to attract the forecasted demand, compete for target markets, and serve its customers at the rate levels that are required to generate an adequate return on the project investments. It also determines the financial feasibility of each project alternative based on agreed metrics, including payback period, the accounting return on investment, the net present value of the net free cash flows, earnings before investment taxes and depreciation, or earnings before investment taxes, depreciation, and amortization, and the pre-tax internal rate of return. Impact analysis determines the institutional, social, economic, and environmental impacts of each project alternative on its surrounding and stakeholders and determine whether these impacts are viable. And risk analysis studies the sensitivity of each project alternative to potential variances in projected conditions such as volume rates and capital investment cost. Physical and operational performance. Physical and operational performance features such as capacity and productivity can be based on refined static assessment of capital and operating resources. Not included in the toolkit discussion are more powerful tools available to the analyst, including simulation, system dynamics, queuing theory, and optimization algorithms. Those tools are used frequently in the assessment of new projects as they require more sophisticated decision-making to justify ever larger investment across the world. Capital resources are frequently tied to elements that increase or sustain the operational performance of a port. Capital resources are studied as waterfront operations and landside operations and supporting facilities. Number of berths, cranes, cargo space, storage, and passenger density are some of the concepts that have large impact in the operational efficiency of the port. For a more thorough list of examples of waterfront, landside, and supporting capital resources, please refer to Exhibits 2.2, 2.3, and 2.4 on pages 2.2 and 2.3 of the toolkit. It is important to consider the definition and impact of phase-dependent project alternatives. Sequencing the implementation of improving these resources defines the implementation schedule of each project alternative and structures capital expenditure forecast. These sequences may change, increase, and decrease the port capabilities and cash flows. The sequencing should be considered to improve the feasibility of the project by allowing not all the work and not all the economic resources to be done at the same time, maintaining or improving regular operations as much as possible while in the construction phases. Estimate the capacity, productivity, and resource requirements of each project alternative and its phases, both during construction phases and during operational phases when the improvements are utilized. The reduction in capacity and/or productivity during this time may influence potential revenue as well as variable operating expenditures. Operating resources. During port operations, a range of resources are deployed that may include, but not limited to, operating workforce, management labor, fuel, power, other utilities including water, communications, and data, machine supplies, and replacement parts. The utilization of operating resources influences the estimation of capital resources and the magnitude of fixed and variable operating expenditures for each project alternative. Capacity and productivity. The enhancement of port performance capabilities, such as throughput capacity, is a function of capital and operating resources and the rate at which those resources are used. The productivity rate of a resource generally has two components: physical space and time. With regard to physical space, the analysis must recognize that in addition to physical space actually in use, empty space maintains fluidity and allows the facility to operate at adequate productivity. Sufficient space is also necessary to sustain accessibility to objects that must be handled or processed. With regard to time, the analysis must recognize that demand is uneven over time and that physical space has been reserved to allow efficient service of peak conditions. Not included in the toolkit are the capacity to create simulation and queuing models that accounts for the utilization of space and the time to respond, and how variability in demand affect the utilization and throughput of the port's resources. These techniques should not be oversight, as they represent an affordable insurance to know a closer to reality assessment of the operational impact of the project alternatives. For example, the toolkit suggests the analysis of berth availability when vessels arrive, even if their scheduled reliability is low, and to take into account seasonal variations in call durations caused by changes in vessel exchange rates. Also suggests assessing the level of utilization that is consistent with maintaining the efficiency and flexibility of the port. This assessment using static models can be insufficient to depict the impact on customer service both on maritime and landside port users. Simulation is affordable and readily available as a tool for larger projects. Market and financial performance. The market and financial performance of a project considers the costs and the benefits to the customer. Customer benefits in the form of lower costs for beneficial cargo and owners, shipping lines, railroads, truckers, warehouse, distribution centers, operators, and other logistics service providers make a port a more attractive place to conduct business and support sustainable revenue streams, lease payments, per unit charges, etc. Port owners must therefore consider not only their own market and financial structures, but also those related to a larger global supply chain. Revenue forecast. Port revenues associated with a project are often heavily dependent on activity-based drivers such as quantity of passengers and/or cargo handled, number of duration of ship calls, and days of storage. Project revenue forecasts are developed in part from the predicted increase in activity generated by a project. Project revenues can also vary widely depending on fixed or variable rate structure, customer benefits, competitive dynamics, and port ownership. The revenue forecast preparations generally requires consideration of a range of complex factors with uncertain outcomes, make adjustments for risk, which will be required by credit rating agencies. As described in the System Dynamics section of this course, project alternative definitions affect cash flows, which in turn may affect project alternative definitions. Cash flow modeling. A life cycle cash flow analysis reflects projected revenues generated by anticipated volumes and costs from project implementation. Costs are typically separated into two categories for financial modeling: capital expenditures, CapEx, and operating expenditures, OpEx. CapEx are typically split into initial costs of constructions and equipment, and ongoing costs of renewal and replacement, R&R, of these assets, sometimes known as periodic, capital, or life cycle maintenance. OpEx are typically split into fixed costs that are independent of throughput volume and variable costs that change with the throughput volume. Financial performance of each project alternative is measured with metrics such as return on investment, payback period, net present value, or internal rate of return. Equally important to a project financial performance, it is public benefit, particularly if the project relies on federal aid. Efforts to maximize project revenue should be balanced with attention to social, economic, environmental, and other impacts. Capital expenditures, CapEx. Infrastructure development or redevelopment and equipment acquisition are the primary capital expenditure investment that comprise CapEx schedules. Depending on project alternative, capital investments in new infrastructure, equipment, renovations and retooling, and/or major asset replacement trigger the sequencing of costs in a CapEx schedule. Replacement of capital assets is driven by an asset reaching its useful life, while new investment is driven by needs identified by gap analysis. Infrastructure. Development of major port infrastructure such as channels, berth, wharves, storage areas, storage structures, passenger facilities, buildings, truck gates, maintenance facilities, support facilities, and intermodal rail yards are examples of infrastructure capital developments that include an initial cost over a given useful life. Costs of these assets are estimated at various stages of project design. At a conceptual level, cost contingencies of up to 30% to 50% may be used due to the unknown conditions at a project site. At the final design stages of a project, cost contingencies may be close to 5% to 10%. Infrastructure CapEx items typically include the construction cost, planning studies, permitting, design services, and construction management. Useful life of infrastructure is typically 30 to 50 years plus, depending on the item. Equipment. Acquisition of port equipment such as quarry cranes, bulk load arms, liquid or dry, conveyors, gangways, container handling equipment, forklifts, trucks, vehicles, and locomotives are examples of equipment CapEx items. Contingency for acquisition, delivery, and installation of equipment is usually in the range of 5% to 15%, or may be set to 0% if recent port-specific pricing is available. Useful life for port equipment typically ranges between 10 and 25 years, depending on the class of machine and the rate at which it is being used. Renewal and replacement R&R, life cycle cost. Most major assets have an option to renew on a regular cycle or at key points in their aging process. There is a trade-off between the initial infrastructure or equipment cost and design and the asset life and hence life cycle cost. For longer projects, the cash flow model may need to reflect multiple rounds of R&R at different intervals for different project elements. Equipment installation frequently involves a time sequence of payments tied to initial ordering, material acquisition by the supplier, assembly, delivery, and acceptance. Operating expenditures. OpEx are related to throughput volume and are typically forecasted in four categories: fixed cost, labor, energy, and routine maintenance. Generally, cost rates for each category are projected from historical figures, and cost total are estimated based on the volume, productivity, and operational deployment of machines and related resources associated with each project alternative. Fixed operating cost. Lease and contractual costs are easy to establish. Most other fixed operating costs, such as insurance, administration, or management fees or salaries, and advisor costs, can be extrapolated from existing precedents. Operating labor. Quantities of labor positions are estimated by work rules, and forecasted labor needs are driven by demand forecast volumes. Labor rates include raw pay rates, overhead, and margin, and may vary depending on the location and type of labor deployed. Terminal operators and labor unions are helpful sources of labor rates if historic values are not available. Energy. Fuel and electricity are the two primary forms of energy used in ports to operate equipment, provide lining, and enable the use of communications. Equipment manufacturers can frequently help with fuel and energy consumption rates. Utility providers and fuel vendors are good sources for cost rates. Routine maintenance. Preventive and reactive maintenance are estimated in similar ways and may be estimated together if a combined rate is available. Consumables include items such as parts, lubricants, tires, and supplies. If technology changes are implemented in a project alternative, unit operating cost rates may also change. Impacts. Potential impact should be considered throughout the project definition process to increase certainty that the likely range of impacts fall within acceptable bounds. Potential mitigation measures for anticipated and avoidable negative impacts should also be identified and integrated into the project alternatives. Identify and measure the direct and indirect impacts of each reasonable alternative in response to existing and projected institutional, social, economic, environmental, regulatory, and/or physical conditions. Direct impacts are manifestation of the use of the port's resources by the port actors. Indirect impacts affect stakeholders outside of the port, such as neighboring communities and drivers on the nearby public roads. Induced impacts are broader secondary effects of the overall operation of the port, where a direct tie cannot be made to a particular resource or actors. Institutional and port user impact. Each project alternative may produce a range of impacts on the port's institution, requiring the port owner to respond with deployment of mitigating resources. The port customers and users will have an influence on the competitive attractiveness of any project. A quantitative and/or qualitative assessment based on discussions with the port stakeholders should be undertaken to assess project influences. Social impacts. Port projects can have complex effects on their host communities, including positive or negative impacts on land use, traffic, natural resources, etc. Identify and measure the wide range of social, public and private, impacts, including state of good repair, livability, economic competitiveness, sustainability, and safety for each project alternative. The effects in each of these categories can be translated into monetized equivalents as part of a benefit-cost analysis. The monetized benefits are calculated over a period of 20 to 30 years, discounted back to net present value, and compared to project costs to generate a benefit-cost ratio. Importantly, the factors considered in a financial analysis, direct receipts, an economic impact analysis, jobs, wages, taxes, etc., are excluded from benefit-cost analysis, since these are usually just restatement of the direct economic benefits of a project. Economic impacts. Economic impact analysis is used to measure the direct, indirect, and induced effects of each project alternative. Economic impacts must be carefully considered as direct transportation benefits are often double counted and can greatly overstate the actual benefits of a project alternative. Many times, economic impacts are only transferred from other ports, and analysis must be careful not to double or triple count benefits in their analysis. Typically, temporary impacts during project implementation and long-term or sustained impacts following an operational period are analyzed separately using an input-output model. Many such models exist, including the Marat's Port Kit model, as well as many private sector packages. Information on construction acquisition costs, cargo passenger activity, and other factors are used as key variables in these models that estimate direct jobs, indirect and induced jobs based on spending from direct jobs and related measures such as personal income from wages and taxes paid. Input-output models are able to differentiate these effects within individual counties and states, as well as the U.S. as a whole, based on the location and construction and improvements. More customized economic impact analysis approaches consider the population of a port-dependent stakeholders. Environmental impacts. Early identification and assessment of potential impacts to the human and natural environment is critical to the success of any project. The risk of not undergoing proper environmental review can be serious, including lawsuits and future distrust by institutions and stakeholder community groups, as well as significant delay and added expense for projects. Port owners should engage with their state Department of Transportation and NPOs early in the planning process to determine the environmental review process for their project. Projects that include federal action will fall under NEPA guidelines. Federal action includes funding, permits, policy decisions, facilities, equipment, and employees. Projects that do not include any federal action will still need to follow the environmental review process required by their state and locality. Some projects will need to comply with requirements from federal, NEPA, state, and local governments. Most state environmental agencies follow the same general process as NEPA, but each will have its own terminology and requirements. The Environmental Protection Agency Port Compliance Tool provides more information for port owners on environmental compliance with state and federal regulation. Exhibit 212 provides a list of the primary federal agencies that may have environmental authority or influence over a given port project. Risk. Risk is a key concern to any investor, whether public or private. The ever-present trade-off between risk and return is unavoidable, and where a project alternative has a high level of risk that needs to be reflected in the required return discount rate or in specific downside sensitivities that reflect the impact of those risks. Risk can be addressed in two key ways. Risk mitigation, where the measures are put in place to reduce the chance of them occurring. Risk sharing or transfer, where the contracts allocate all or some of the risk to the construction contractor, terminal operator, or other third party, as long as the price charged for this transfer is economic. Risk analysis is discussed in more detail and the different courses in the program. Evaluate. Port projects are often undertaken in complex operational, commercial, and institutional conditions and in a sensitive natural and urban environment, each with its own requirements. Accordingly, there are a number of techniques and criteria that may be used to evaluate port project alternatives. Much of this feasibility module focuses on quantitative measures such as throughput capacity, revenue projection, and financial performance, as well as environmental and economic impacts. Some performance measures cannot be mathematically quantified. They are open to human judgment. Qualitative measures such as compatibility with community interest, availability of skilled workforce, and project flexibility are examples of the type of evaluation criteria that are subject to a wider variation in interpretation and priority. In such cases, very clear value statements must be made and allow the team to clearly judge the alignment between project features and qualitative measures. Selection of a best project frequently requires deliberation and trade-offs of a broad array of performance, impact, and risk elements. The results of stakeholder outreach must be considered, and the interests of all parties truthfully and transparently balanced. Project evaluation approach. Depending on the focus and purpose of the evaluation, an approach may involve the application of a single measure, a combination of different quantitative and qualitative measures, or customized according to specific requirements. Common types of evaluation techniques used by the port industry to assess project feasibility include cash flow evaluation, benefit cost analysis, and multi-criteria evaluation. Other evaluation approaches may be required for port owners pursuing funding and financing for their project. Cash flow evaluation. Cash flow is essential in determining the financial viability of an investment. Evaluation measures that are still used for high-level screening of projects include payback period and accounting return of investment. Both have serious flaws and have been superseded by analyses that are more accurately reflect the difference in future cash flows generated by a project. Key to the measurement of return over a number of future years is the principle known to economists as time value of money. These methods are based on a simple idea. Today's money is worth more now than the same amount received in the future because today's money can be invested. Future cash flows from alternative investment are discounted at the opportunity cost of capital in order to determine whether it provides a better return. These can also be explained as interest loss by taking money out of the account or similarly save investment to fund a project. Another way of looking at this concept is the investor needs to borrow money. It is considered what future money will be worth now after taking account of the cost of the borrowing. Net present value. The net present value of cash flow is the sum of those current values of all the future revenues less future costs, including the cost of the investment. If totaled over the life of a project of investment, it gives the project value in current money. The value is highly dependent on the discount rate used to reflect the opportunity cost of capital or cost of borrowing and any addition to reflect risk. Internal rate of return, IRR. The internal rate of return avoids the need to choose a discount rate as it turns the proposal around and looks for the discount rate at which the net present value of the initial investment plus the future cash flow over the analysis period is zero. It is typical to compare the project life internal rate of return to a target holder rate to screen project alternatives with similar risks. Internal rate of return also has its challenges when particular high revenue growth is expected and the evaluation period is long. In those cases, the initial and annual running yield may also be used to compare different options as investors have limits to their patience in waiting for returns. Benefit cost analysis. A formal benefit cost analysis is frequently an essential step in gaining project funding from outside sources. In those cases, the initial annual running yield may also be used to compare different options as investors have limits to their patience in waiting for returns. Benefit cost analysis. A formal benefit cost analysis is frequently an essential step in gaining project funding from outside sources. A benefit cost analysis is an evaluation framework to assess economic advantages, benefits, and disadvantages, cost, of each project alternative. Benefits and costs are broadly defined and are quantified in monetary terms to the extent possible. The overall goal of the benefit cost analysis is to assess whether the expected benefit of a project alternative justify the cost from a national perspective. A benefit cost analysis helps to discern the net welfare change created by a project alternative, including cost savings and increases in benefits, as well as benefits where the cost can be identified, for example, project and capital cost, and welfare reductions where some groups are expected to be made worse off as a result of a project alternative. Applicants for federal funding have been required to support their applications with a formal benefit cost analysis prepared according to the U.S. Department of Transportation Benefit Cost Analysis Resource Guide. This methodology includes the following analytical activities: assessing benefit with respect to each of the 5 long-term outcomes stated of good repair, livability, economic competitiveness, sustainability, and safety defined by the U.S. Department of Transportation. U.S. Department of Transportation recommended monetized values for reduced fatalities, injuries, property damage, travel time savings, and emissions while relying on best practices for monetization of other benefits. Discounting future benefit and costs with real discount rates of 7% and 3%, consistent with U.S. Department of Transportation guidance, and dividing the total discounted benefits by the total discounted cost to determine the benefit cost ratio. With the continuation of the Tiger program and the dedicated freight funding under the FAST Act, port owners should be familiar with the principles of a formal benefit cost analysis, as it is expected to remain important. Multi-criteria evaluation, a multiple criteria decision-making approach, facilitates the analysis of the complex trade-offs between project alternatives. Both qualitative and quantitative measures, including cash flow and benefit cost values, can be combined into an evaluation process to allow for comprehensive assessment of each alternative. A multi-criteria evaluation approach could include the criteria categories such as financial, net present value, internal rate of return, revenue potential, debt service, coverage ratio, CAPEX, OPEX, life cycle cost per unit handle, etc. Economic impact, direct, indirect, and induced, benefit cost ratio, operational capacity, vessel service performance, landside transportation service performance, etc. Environmental, project risk. Weight each criterion relative to the other criteria to prioritize the related level of importance. The multi-criteria evaluation matrix is used to distinguish the relative scores of each project alternative, and it performs against each criteria. Reasonable alternatives comparison. The outputs of the quantitative or qualitative measures of the project alternatives are ranked and compared against each other. The ranking and comparison should clearly demonstrate that one alternative is preferable to the base case and to other reasonable project alternatives considered during the planning process. Recommended project. Once the project alternatives have been compared, ranked based on separate and other cumulative criteria scores values embedded with stakeholders and project decision makers, the project team should agree on a recommended project. Consider incorporating the higher performing attributes from the other alternatives into the recommended project to optimize feasibility. Integrating the high performing attribute into the recommended project will require an evaluation of the impact. Once the recommended project's feasibility is optimized, it is ready to be considered for alternative financing and funding approaches.